Hello there, and welcome to the Sleepy Science Channel. Tonight's journey takes us down into the hidden fabric of reality, to a place smaller than atoms, smaller than protons, where the building blocks of the universe may not be particles at all. It's a theory that suggests beneath everything we see lies an invisible symphony of tiny vibrating strings. These are thought to be so small that if an atom were the size of the solar system, a string would still be invisible. Their vibrations could decide whether something appears as an electron, a photon, or even the force of gravity itself. And in order for the math to work, the universe may need hidden dimensions, entire directions of space curled up beyond our sight. If you enjoy these gentle journeys, consider liking and subscribing, or share a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But for now, you don't need to do anything at all. Just settle in, let your breathing grow steady, and imagine those tiny strings humming quietly in the darkness, weaving the universe with their hidden music. Now, let's begin. String theory proposes that what we call particles are illusions, shadows cast by vibrating strings in unseen dimensions. When we look deep into matter, physics tells us the world is built from particles, electrons, quarks, photons. But string theory suggests that these may not be the ultimate ingredients at all. Instead, they could be like the flickering shadows on the wall of a deeper reality. At the smallest possible scales, each particle is thought to emerge from a tiny string vibrating in patterns too small for us to see. An electron is one vibration, a quark another, a photon yet another. What we call particles in this view are simply the outward appearances of something more fundamental, hidden strings playing a silent, unseen music in dimensions beyond the ones we know. A single string may be so small that if an atom were the size of Earth, the string would still be invisible. The scale of a fundamental string is almost impossible to imagine. Atoms themselves are already mind-bendingly small, each one made of protons and neutrons bound with electrons. Yet if we somehow magnified an atom until it was as large as the entire Earth, the string inside would still be far too tiny for us to glimpse. Strings exist on the scale of the Planck length, about 100 billion times smaller than a proton. At that level, space itself is thought to become grainy and uncertain, dissolving into quantum foam. It means that if strings are real, they are not just small. They are as far below atoms as atoms are below galaxies. Invisible threads vibrating at the foundation of existence. Each possible vibration of a string maps to a different particle, from electrons to photons to gravitons. Imagine a violin string, capable of producing many notes depending on how it vibrates. Now shrink that idea to the smallest possible scale. In string theory, a single fundamental string can vibrate in countless modes. Each mode is not a sound, but a particle. One vibration pattern appears as an electron. Another becomes a quark. Another still emerges as a photon, the particle of light. Most astonishing of all, one special vibration corresponds to the graviton, the hypothetical quantum particle of gravity. This is why string theory excites physicists so deeply. It offers a single object, the string, whose infinite range of vibrations could explain every known particle and force. Instead of many separate building blocks, the universe may be written from one instrument, one cosmic string whose notes give rise to all of reality. Some strings form endless closed loops, while others dangle open with free ends. Not all strings are alike. Some are closed, curling around into endless loops that have no beginning or end. Others are open, with two free ends that can move, join, or even anchor themselves to higher dimensional objects. The difference is profound. Closed strings naturally give rise to the graviton, and therefore to gravity. Open strings, by contrast, are linked to the particles that make up matter and forces such as electromagnetism. In the vast landscape of string theory, both types may coexist, weaving together the tapestry of the cosmos. Some may stretch across branes, some may shrink so small they act like point particles. Together, their interplay creates the astonishing variety of matter and energy we see in the universe. Gravity emerges naturally from closed strings, making string theory unique among quantum models. One of the deepest puzzles in physics is why gravity refuses to fit neatly with quantum mechanics. Attempts to quantize gravity using particles like the photon have led to equations filled with infinities. But in string theory, gravity appears not as an afterthought, but as a natural outcome. Closed strings vibrate in a particular way that corresponds exactly to the graviton, the particle that would carry the force of gravity. The smoothness of the string spreads out the violent point-like collisions that would normally cause infinities. Instead of breaking, the math holds together. For this reason, string theory remains one of the most promising ideas for unifying quantum physics with Einstein's curved spacetime. It doesn't bolt gravity on from the outside. It sings it directly from the vibrations of a tiny closed loop. The theory was first discovered by accident, while physicists studied nuclear forces in the 1960s. String theory did not begin as a quest for a theory of everything. In the late 1960s, physicists were struggling to understand the strong nuclear force, the powerful glue that binds quarks inside protons and neutrons. They developed mathematical models that described the observed patterns of particles, but the equations were strange. Buried within them was a solution that behaved as if particles were tiny vibrating strings. At first, this was seen as a curiosity, even a mathematical oddity. The strong force was eventually explained by quantum chromodynamics, and string theory was set aside. But a handful of researchers noticed something remarkable. The string framework seemed to include gravity in a natural way. What began as a failed attempt to explain nuclear physics would later evolve into the most ambitious unification attempt in science. What began as a failed model of particle physics grew into a candidate for a theory of everything. By the early 1970s, string theory had already fallen out of fashion. It did not correctly explain the strong nuclear force, which was now described beautifully by quantum chromodynamics. But hidden within the theory was something far more profound. Physicists discovered that strings predicted not just the known forces, but gravity itself. This meant that string theory could serve as a framework for unifying all of physics, electromagnetism, nuclear forces, and gravity in one package. Slowly, the idea re-emerged, not as a tool for describing protons, but as a sweeping candidate for a theory of everything. Few theories have undergone such a transformation, from discarded failure to one of the most daring visions of the universe ever proposed. String theory insists that the universe has hidden dimensions beyond the three of space and one of time. Our everyday world seems to have three familiar directions: length, width, and height, and one dimension of time. But the equations of string theory cannot work with only these four. To remain consistent, they require extra dimensions curled up beyond our perception. These hidden dimensions are not large like the ones we move through, but compact, coiled so tightly that no microscope could ever detect them directly. They may exist all around us, invisible and silent, shaping the possibilities of how strings vibrate. Without them, the theory simply falls apart. In this way, string theory asks us to imagine a universe far larger and stranger than what our senses suggest. A universe where unseen dimensions lie folded into the very fabric of reality. Most versions require a total of 10 dimensions for the equations to make sense. The number of dimensions is not arbitrary. When physicists worked through the mathematics of string theory, they discovered that the theory only avoids inconsistencies if spacetime has 10 dimensions. Any fewer, and the equations collapse. Any more, and the framework shifts into another form. This result was shocking. It meant that the four-dimensional world we see is only part of a bigger picture. In string theory, 6 additional spatial dimensions must be hidden from view. They may be compact and curled, but they are crucial to making the theory work. Without them, the delicate balancing of vibrations and forces would unravel. 10 dimensions may sound exotic, but within the logic of strings, it is the minimum required for the universe to exist as we know it. In an even deeper extension known as theory, the universe may have 11 dimensions. Just when 10 dimensions seemed bizarre enough, an even stranger idea emerged. In the mid-1990s, physicists discovered that the 5 different versions of string theory were not truly separate. They were all connected by hidden dualities, different faces of the same underlying theory. To account for this unity, researchers proposed an even larger framework, M-theory. In M-theory, the universe does not stop at 10 dimensions, but extends into 11. Strings themselves may be just one-dimensional slices of higher-dimensional branes. The 11th dimension opens up new possibilities for how the universe is structured and for how gravity behaves. Whether M stands for magic, mystery, or mother, it represents a profound leap, a step beyond strings, toward an even more expansive view of reality. These hidden dimensions are thought to be curled up so tightly that no experiment has yet seen them. When physicists speak of extra dimensions, they don't mean vast new directions we could step into. Instead, they imagine dimensions compacted so tightly that they escape our senses entirely. Think of the garden hose. From far away, it looks like a simple line, but up close you see it also curves around in a circular dimension. String theory suggests that the universe may have additional dimensions curled up in ways we cannot resolve, even with our most powerful instruments. They may be smaller than the nucleus of an atom, woven into reality itself. Though invisible, these hidden dimensions are essential. Without them, the mathematics of string theory simply fails. It is a reminder that the universe may be much richer than the flat stage our everyday lives seem to occupy. The shapes of these curled-up dimensions could decide the laws of physics we observe. If hidden dimensions truly exist, their geometry may hold the key to why our universe has the rules it does. In string theory, the way dimensions fold and twist is not arbitrary. Different shapes change the way strings vibrate, and those vibrations determine which particles appear and how they interact. In one shape, electrons may have one mass in another. Their properties could be entirely different. Even the strengths of fundamental forces may be tied to this geometry. It means that the universe we know, with its stable atoms, its chemistry, and its stars, may depend on the invisible architecture of dimensions too small to see. If they were shaped differently, reality itself could have unfolded in a completely alien way. One possible shape, a Calabi-Yau manifold, twists space into intricate folds beyond imagination. To describe the extra dimensions, physicists turn to a strange class of mathematical objects called Calabi-Yau manifolds. These are shapes that curve and fold in 6 dimensions at once, creating intricate structures more complex than anything we can visualize directly. They may look, in a sense, like multi-dimensional origami, with folds upon folds that determine how strings resonate. Each Calabi-Yau space is unique, and the number of possible shapes is staggeringly large, perhaps more than there are atoms in the universe. If one of these manifolds truly describes our universe, it means that the very laws of physics are written into the geometry of invisible folds of space. Though abstract, these mathematical surfaces may be the hidden scaffolding that lets the cosmos exist as it does. Strings can stretch, twist, and vibrate in countless ways, each way revealing a new type of matter or force. The simplest picture of a string is as a tiny thread, but in string theory, that thread can behave in endlessly varied ways. A string may stretch taut like a violin string, or twist in complex loops. It may vibrate in different modes, higher or lower, faster or slower. Each of these possibilities maps to a unique particle or force. This is the heart of why string theory is so compelling. Instead of imagining dozens of unrelated particles, we have one single object, the string, whose movements produce everything else. The universe becomes less a collection of separate pieces and more a single instrument, capable of infinite songs. The diversity of matter, from the electron to the quark to the photon, could all be the music of vibrating strings. The vibrational patterns of strings could explain why electrons, quarks, and photons are all so different. At first glance, particles seem like unrelated species. Electrons circle atoms. Quarks build protons. Photons carry light. Why should these building blocks exist at all, and why should they be different? String theory offers a startlingly simple answer. The differences between particles may not be about what they are made of, but how the same string vibrates. Just as one guitar string can play many notes, one fundamental string may take on many forms. In one mode, it is an electron. In another, it is a quark. In another, a photon. What we see as different categories may be nothing more than the echoes of different notes on the same underlying string. This vision reduces the clutter of nature to a single principle: vibration as the source of diversity. Even the graviton, the hypothetical particle of gravity, appears naturally as a vibration of a closed string. Gravity has always resisted merging with quantum mechanics. Photons fit the equations beautifully, as do gluons and W and Z bosons. But gravity defies quantization, unless strings are real. In string theory, the graviton emerges automatically as one particular vibration of a closed loop of string. No special adjustments are needed. Gravity is simply part of the music. This is why physicists became so fascinated with the theory. It was the first time gravity could be included seamlessly alongside the other forces. If gravitons truly exist, and if they truly arise from closed strings, then string theory may be the missing bridge between Einstein's curved spacetime and the strange quantum world. Strings are measured at the Planck length, a scale far smaller than anything we can probe. The Planck length is the smallest meaningful scale in physics, about 10 to the minus 35 meters. To give a sense of its smallness, imagine stretching a meter stick across the universe, then dividing it into pieces the size of a single Planck length. You would have more pieces than there are atoms in the cosmos. Strings are thought to be roughly this size. No microscope, no accelerator, not even the Large Hadron Collider can hope to see them directly. They are far beyond our technological reach. Yet even though they are hidden, their effects could shape everything we observe. Strings may be too small to touch, but they could be the unseen foundation on which the universe itself rests. At this scale, space-time itself may dissolve into quantum foam, softened by the smoothness of strings. If we tried to zoom down to the Planck length, the smoothness of space-time would vanish. Instead of a continuous fabric, it would froth and boil with fluctuations, a jittering quantum foam where geometry itself ceases to make sense. Point-like particles break down here, their interactions exploding into infinities. Strings, however, spread the chaos. Their finite length smooths out the violence. Collisions are not single points but extended interactions, softening the foam into something manageable. In this way, strings may tame the wildness of quantum gravity, allowing space-time to exist in a consistent, calculable way. At the smallest scales, they provide the order that lets the universe hold together. By replacing points with loops, string theory avoids the catastrophic infinities that plague other quantum theories of gravity. One of the greatest problems in physics is that when you try to describe gravity in quantum terms, the math quickly collapses. Point-like particles colliding in space-time lead to infinite quantities that cannot be renormalized away. String theory replaces points with loops of finite size. When two strings interact, they smear their effects across space, preventing the sharp divergences that ruin point-particle theories. The infinities vanish, replaced by finite results. This is one of the theory's deepest appeals. It doesn't just include gravity. It does so in a way that resolves the long-standing problem of infinities. Strings act as natural regulators of the universe, letting quantum gravity exist without mathematical collapse. Strings are not alone. The theory also predicts extended objects called branes, which can stretch across higher dimensions. Beyond one-dimensional strings, string theory also predicts higher-dimensional objects known as branes. A brane can be two-dimensional like a sheet, or three-dimensional like a volume, or even higher. They can stretch across entire dimensions, anchoring strings and shaping the universe itself. Some theories suggest our own cosmos is a three-dimensional brane floating in a larger multidimensional space. If so, the universe we see could be just one brane among countless others, each with its own strings and particles. Branes extend the vision of string theory beyond threads into entire surfaces, expanding the idea of what the fundamental structures of reality might be. Branes can come in many forms, from two-dimensional sheets to volumes that fill entire universes. While strings are one-dimensional, string theory also predicts the existence of higher-dimensional structures called branes. A brane can be as simple as a flat two-dimensional surface, or as vast as a multidimensional volume that stretches across an entire cosmos. Just as strings can vibrate, branes can bend, twist, and ripple through higher-dimensional space. They may act as anchor points for strings, giving rise to the particles and forces we observe. The word brane is short for membrane, and it emphasizes that the fundamental ingredients of reality might be more varied than threads alone. These extended structures open the door to entire universes built on higher-dimensional scaffolding. In some versions of the theory, branes are as central as strings themselves, forming the stage on which the drama of existence plays out. Our entire cosmos may be a three-dimensional brane floating in a higher-dimensional space. Imagine our universe not as a boundless void, but as a surface suspended within a larger reality. String theory suggests that our cosmos may itself be a brane, specifically a three-dimensional one, embedded within a higher-dimensional space, sometimes called the bulk. Everything we see, from galaxies to atoms, could be confined to this brane, unable to escape its dimensions. The forces of nature may be trapped here as well, except for gravity, which is free to wander into the bulk. In this view, our universe is not the whole of reality, but a slice of it. Other branes could float nearby, carrying their own universes, invisible to us. This radical vision transforms our sense of scale. What we call the cosmos may be just a bubble drifting in a larger, unseen ocean. Gravity might leak off our brane into extra dimensions, explaining why it feels so weak compared to other forces. Compared to the other forces of nature, gravity seems absurdly weak. A single magnet can lift a paperclip against the entire pull of Earth. String theory offers a possible explanation. While the electromagnetic and nuclear forces may be confined to our three-dimensional brain, gravity is not. The graviton, carried by closed strings, can slip free into extra dimensions, spreading its strength across the bulk. To us, confined within the brain, gravity appears diluted and feeble. But in the higher dimensional reality, it may be just as strong as the other forces. This idea not only explains a long-standing puzzle, but also suggests that experiments sensitive enough might one day detect the faint leakage of gravity into extra dimensions, a glimpse into the hidden bulk scowl beyond our universe. Strings with open ends can be tethered to branes, making them fundamental to how matter behaves. In string theory, not all strings are closed loops. Some are open, with two free ends. These open strings cannot drift aimlessly. Instead, their ends are often bound to branes, attaching them like tiny anchors. This connection may be more than mathematical. The particles we know, such as electrons and quarks, could arise from open strings tied to the brain of our universe. Their properties would be shaped not only by how the string vibrates, but by how it connects to the brain itself. In this way, branes and open strings work together to generate the rich variety of matter in the cosmos. We may exist quite literally as the result of strings bound to the surface of a higher dimensional brain, resonating in silence. When branes collide, they may release bursts of energy on a cosmic scale. Branes are not static objects. Like vast sheets or volumes suspended in higher dimensions, they can drift, ripple, and even collide. When two branes crash into one another, the energy released could be colossal, dwarfing anything we can imagine. These collisions might reshape entire universes, creating bursts of matter and radiation on a scale beyond comprehension. Some models of string cosmology suggest that such events are not rare, but natural consequences of brain dynamics. To us, confined within a brain, the aftershock of such a collision could look like the birth of everything we know. Instead of being a singular point-like explosion, the beginning of our cosmos may have been the echo of a higher dimensional collision in the bulk. Some cosmologists believe the Big Bang itself could have been caused by two branes colliding. The mystery of the Big Bang has long puzzled science. How did space and time themselves ignite in a single moment of creation? String theory offers a bold answer. Perhaps the Big Bang was not the beginning of everything, but the result of two branes colliding in a higher dimensional space. In this view, universes can be born whenever branes crash together, filling them with energy and matter. The echo of that cosmic impact could be the expanding universe we inhabit. This ekpyrotic model, as it is sometimes called, reframes the Big Bang not as a singular event, but as part of a larger cycle of brain interactions. If true, our universe may carry subtle scars, traces in the cosmic background radiation left behind from the colossal impact that gave birth to our world. String theory offers the first serious framework that unifies all four fundamental forces of nature. Physics has long been split between two powerful but separate frameworks. Quantum mechanics explains the three non-gravitational forces: electromagnetism and the strong and weak nuclear forces. Einstein's general relativity explains gravity, yet the two refuse to fit together. String theory is the first theory that naturally contains all four forces within one framework. Strings, through their vibrations, can give rise to both photons and gravitons, gluons and W bosons, binding all interactions into a single picture. It is the closest science has come to the dream of a unified theory of everything. Though unproven, the possibility that one idea could explain the entire spectrum of nature is breathtaking. It means the complexity of forces may all reduce to the resonances of tiny strings in hidden dimensions. It weaves together electromagnetism, the strong and weak nuclear forces, and gravity itself. The four fundamental forces appear different in strength and behavior, but string theory suggests they are variations of the same underlying fabric. Electromagnetism lights our world and drives chemistry. The strong force binds quarks into protons and neutrons. The weak force shapes radioactive decay. Gravity pulls planets into orbits and binds galaxies together. In conventional physics, these forces are described separately, each with its own rules. In string theory, they arise from the same source, different notes in the vibration of strings. This weaving of forces into a single story fulfills a dream first imagined by Einstein, who longed to see nature's laws unified. In string theory, the universe ceases to look fragmented and begins to look like a single woven tapestry of vibrating threads. The unification dream was pursued by Einstein for decades, and string theory may finally achieve it. Albert Einstein spent the last decades of his life searching for a unified field theory, a single framework that could explain gravity and electromagnetism together. He did not succeed, and quantum mechanics soon revealed even more forces to account for. But his vision was not in vain. String theory represents the most promising realization of Einstein's dream. It brings all forces under one roof, not by forcing them together, but by showing they emerge naturally from one principle, the string. Though Einstein himself did not live to see it, the theory he longed for may have been waiting in the vibrations of hidden dimensions. The quest for unification is still unfinished, but with string theory, it has never felt closer to complete. Supersymmetry is essential to string theory, pairing every particle with a heavier, unseen partner. For string theory to work, the equations require a hidden symmetry beyond those we already know. This symmetry, called supersymmetry, pairs every known particle with a partner of opposite spin. Electrons would have selectrons. Quarks would have squarks. Photons would have photinos. These superpartners have not yet been observed, but they play a crucial role in stabilizing the mathematics of the theory. Without them, the vibrations of strings would not line up consistently. Supersymmetry also offers solutions to puzzles in particle physics, such as the nature of dark matter. If superpartners are eventually discovered in experiments, it would be one of the strongest pieces of evidence that string theory reflects reality. Until then, supersymmetry remains one of its boldest and most hopeful predictions. These partners, such as the selectron or squark, have not yet been detected in experiments. Supersymmetry predicts that every known particle should have a heavier partner, the selectron for the electron, the squark for the quark, the photino for the photon. Yet despite decades of searching, none have yet been found. The Large Hadron Collider has probed energies high enough to rule out many early predictions. Still, supersymmetry might reveal itself at higher energies, just beyond our reach. The absence of discovery so far does not disprove string theory, but it leaves one of its most striking predictions unconfirmed. For physicists, this is both frustrating and thrilling. The partners may be hiding in plain sight, waiting for technology advanced enough to glimpse them. If they do exist, they would open the door not only to string theory's validation, but to entirely new realms of matter and energy. Discovering supersymmetric particles would be one of the strongest confirmations of string theory. Evidence for supersymmetry would be a landmark moment in physics. It would show that nature is built on a symmetry deeper than anything we have yet observed, one that links matter and forces in elegant pairs. Finding even one superpartner, such as a selectron or neutralino, would not only confirm supersymmetry, but provide powerful support for string theory itself. It would mean that the hidden scaffolding predicted by the theory is real. Experiments could then begin mapping this new layer of reality, testing whether string vibrations truly give rise to both ordinary particles and their superpartners. Such a discovery would ripple across physics, reshaping cosmology, particle physics, and our search for dark matter. For now, it remains a dream, but one that drives enormous effort at particle accelerators worldwide. Supersymmetry also cancels dangerous quantum instabilities that would otherwise wreck the theory. Without supersymmetry, string theory's equations fall apart. Quantum fluctuations would pile up uncontrollably, making the theory inconsistent. Supersymmetry acts as a balancing principle. The contributions from ordinary particles and their superpartners cancel one another, smoothing out the infinities that would otherwise appear. This symmetry doesn't just make the math elegant, it makes the math possible. It allows string theory to survive at the Planck scale, where spacetime and quantum mechanics collide most violently. Supersymmetry is like a tuning fork that keeps the vibrations of strings in harmony. Without it, the delicate balance would collapse, and the theory could not even get off the ground. Even though its particles have not yet been seen, supersymmetry's role in stabilizing the equations gives physicists reason to believe it may truly exist in nature. Without it, string theory's equations simply cannot remain consistent. Mathematics is unforgiving. When physicists tried to build string theory without supersymmetry, the results quickly unraveled. Inconsistencies appeared. Negative probabilities crept into the calculations, signaling that something was deeply wrong. Supersymmetry is not optional. It is required for the theory to make sense. This is why string theory is often referred to as superstring theory. Without supersymmetry, the framework collapses under its own contradictions. With it, the equations align into a coherent structure capable of unifying all forces. It is a reminder that in physics, beauty and necessity often overlap. The symmetry that makes the theory elegant is also what makes it possible. If nature truly obeys string theory, then supersymmetry is not just a mathematical trick, it is a hidden law woven into the fabric of the universe. Over time, physicists discovered that there are several kinds of string theory. As string theory developed, it did not emerge as a single neat framework. Instead, physicists found that the equations allowed for multiple versions, each with slightly different properties. At one point, there were 5 consistent formulations, each describing a different kind of string or symmetry. For years, this was confusing. How could there be 5 theories of everything? Which one, if any, was correct? Each had strengths, each had weaknesses, and they did not seem to reconcile with one another. For some, this looked like a flaw. But as the field matured, it became clear that these versions might not be rivals at all, but different perspectives on the same deeper truth. These include Type 1, Type IIA, Type IIB, and 2 heterotic versions. The 5 consistent theories came to be named as Type 1, Type IIA, Type IIB, heterotics are 32, and heterotic E 8 times E8. Each has a unique character. Type 1 involves both open and closed strings. Type 2A and IIB differ in the way strings vibrate and the kinds of supersymmetry they allow. The heterotic versions are stranger still, combining properties of 2 types of strings into one hybrid form. For decades, physicists puzzled over which, if any, reflected the real universe. Their existence seemed to fragment the dream of unification. But later discoveries revealed that these differences were not contradictions, but pieces of a larger puzzle, hints that something more comprehensive lay beyond them all. At first, They seemed like competing and contradictory possibilities. To an outside observer, the existence of 5 string theories might have looked like chaos. Each had beautiful mathematics, but none seemed to match the others. They looked like mutually exclusive blueprints for the universe. If one was right, the others had to be wrong. The idea of a single, unifying framework seemed to be slipping away. For a time, critics argued that string theory was multiplying, not simplifying, the laws of physics. How could there be 5 different theories of everything? But within the contradictions lay hidden clues. The very differences that seemed irreconcilable would soon reveal a secret, that these theories were not rivals, but reflections of one deeper structure. Then came the realization that they were secretly linked by hidden dualities. The breakthrough came when physicists discovered that the 5 string theories were connected through surprising transformations known as dualities. Under certain conditions, what looked like one theory could transform into another. A weakly interacting string in one version might look like a strongly interacting one in another. A compactified dimension in one could reveal the geometry of a different theory. These links meant that the theories were not isolated islands, but part of a single interconnected continent. Dualities showed that the boundaries between them were illusions, and that they were all shadows of a deeper truth yet to be named. These dualities showed that what looks like one theory in one regime is another theory in disguise. In physics, duality means that 2 very different descriptions can, in fact, represent the same reality. In string theory, this principle is taken to an extraordinary level. A string theory that looks weak and simple may secretly be equivalent to a different theory that looks strong and complex. What appears as a particle in one framework may be a brane in another. The transformations are so complete that entire theories once thought distinct turn out to be disguises for each other. This realization was revolutionary. It suggested that the 5 versions of string theory were not separate at all, but windows into a single underlying framework, a truer, deeper theory that would become known as M-theory. This surprising web of connections led to the birth of M-theory. In the mid-1990s, the scattered pieces of string theory were gathered under one name, M-theory. It emerged from the discovery that the 5 consistent string theories were actually different aspects of a single 11-dimensional framework. Strings were only part of the story membranes, and higher dimensional objects joined them. The ME in M-theory has been said to stand for magic, mystery, or mother, reflecting its enigmatic power. This unifying vision was called the second superstring revolution, and it redefined the field. What once seemed fractured became whole. Instead of 5 competing theories of everything, physicists now had one. Vast, flexible, and capable of describing reality in ways no single version ever could. M-theory suggests that all string theories are just different limits of one deeper framework. When physicists first discovered the 5 distinct string theories, it seemed like a flaw. How could there be 5 separate theories of everything? But M-theory turned this confusion into a revelation. It showed that each version was not truly separate, but a special case, a limit of a deeper, more complete framework. Just as different perspectives can reveal different sides of the same object, the 5 string theories are simply views of a single, hidden whole. This deeper structure is M-theory, an 11-dimensional framework in which strings, branes, and dualities all coexist. The many theories that once competed now appear as interconnected fragments, united under a single vast umbrella. In M-theory, strings themselves may be slices of larger objects called membranes. M-theory broadened the vision of what fundamental objects can be. Strings, once thought to be the foundation of everything, may themselves be pieces of something larger. In this deeper framework, higher dimensional membranes, called branes, take center stage. Strings may simply be the one-dimensional cross-sections of these larger structures. Just as a shadow reveals only part of the object casting it, strings may be the thin traces of branes moving through higher dimensional space. This perspective expanded the possibilities of the theory enormously. No longer limited to threads, reality could include sheets, volumes, and even more exotic extended objects. The universe, in this view, is richer than anyone imagined when strings alone were first proposed. The M in M theory has been said to stand for magic, mystery, or mother. Physicists often disagree about what the M in M theory really means. Some say it stands for magic, reflecting the almost miraculous way the theory unites its predecessors. Others prefer mystery, acknowledging how little we still understand about its full form. Still others call it mother, suggesting it is the mother of all theories, the framework from which all others emerge. The truth is that no single meaning has ever been fixed. The ambiguity reflects the theory itself, powerful, suggestive, yet not fully understood. The theory remains as enigmatic as its name, a promise of a deeper reality still waiting to be revealed. M theory expanded the possible dimensions from 10 to 11. In superstring theory, consistency required 10 dimensions, 9 of space and 1 of time. But M theory goes further. Its mathematics shows that the complete picture needs 11 dimensions. That extra dimension opens up a new landscape of possibilities. Strings may be reinterpreted as slices of higher dimensional branes, and entire new structures become possible. 11 dimensions may sound abstract, but for physicists, it is a sign that the deeper theory is broader and more flexible than any of its pieces alone. It is as if the puzzle of reality required one more piece, hidden until the 5-string theories were united. With 11 dimensions, the theory reaches beyond the already exotic world of strings into a realm even stranger and more expansive. The discovery of dualities was so revolutionary, it became known as the second superstring revolution. The mid-1990s marked a turning point in theoretical physics. When dualities revealed that the 5-string theories were connected, the field was transformed overnight. What had seemed fragmented and uncertain became unified and vibrant. Physicists called this moment the second superstring revolution. New insights flooded in. M theory, branes, and holography emerged from this fertile period. For many, it was the most exciting intellectual movement since Einstein reshaped space and time. The revolution didn't solve all of string theory's mysteries, but it changed its trajectory forever. From then on, string theory was no longer a collection of competing models. It was a single evolving vision of the deep structure of reality. String theory gave birth to the holographic principle, one of the most radical ideas in physics. Among the most surprising insights to emerge from string theory is the holographic principle. It suggests that the three-dimensional world we experience may actually be described by information stored on a two-dimensional surface. Just as a hologram encodes a three-dimensional image on a flat plate, the universe itself may be a projection from a more fundamental boundary. This idea was first glimpsed in the study of black holes within string theory, where paradoxes about information led to startling conclusions. The holographic principle has since become one of the most influential concepts in theoretical physics, reshaping how scientists think about spacetime, gravity, and quantum mechanics. The holographic principle suggests that everything in the universe may be encoded on a distant surface. Imagine that everything we see, every star, every planet, even our own lives, could be described by data inscribed on the edge of the cosmos. That is the bold suggestion of the holographic principle. In this view, the universe is like a vast hologram. The three-dimensional reality we experience is a projection, while the true information lies on a two-dimensional surface, far away. This idea is not mere science fiction. It arises naturally from the mathematics of string theory and black holes. If correct, it would mean that reality itself is not what it seems. The universe would be like a cosmic movie, with the film strip hidden on a surface we cannot reach, projecting the world we know. This insight first arose from studying black holes in string theory. The seeds of the holographic principle were planted in the study of black holes. Classical physics suggested that information falling into a black hole would be lost forever. But quantum physics insists that information cannot be destroyed. String theory provided a bridge. It showed that black holes could be described by strings and branes in ways that preserved information. The surprising result was that the information seemed to live not inside the black hole, but on its surface, encoded on the event horizon. This realization hinted at a general rule. Perhaps all of space and time could be described by data on boundaries. From black holes came a universal lesson: the holographic nature of the cosmos itself. Black holes seem to destroy information, defying quantum law. For decades, black holes posed one of the greatest puzzles in physics. According to Einstein's equations, anything falling into a black hole would be lost beyond the event horizon, never to return. But quantum mechanics states that information cannot be erased from the universe. These two principles clashed violently. If black holes destroyed information, quantum theory would be broken. If information survived, relativity seemed incomplete. The paradox stood unresolved until string theory entered the picture. By reimagining black holes as made of strings and branes, it became possible to preserve information in a new way. What seemed like destruction turned out to be transformation, reshaping how scientists understand both black holes and the fabric of reality. But string theory showed that information could be preserved on the horizon like a hologram. The breakthrough came when physicists calculated black hole entropy using string theory. They counted the possible states of strings and branes that could form a black hole, and the result matched the entropy predicted by thermodynamics. This meant the information was not lost but stored, smeared across the event horizon. To an outside observer, the horizon acts like a screen, encoding everything that has fallen in. Instead of being destroyed, information is preserved holographically. This resolution was not only a triumph for string theory, but also the foundation for the broader holographic principle. It suggested that horizons, whether around black holes or around the universe itself, may hold the true record of reality. This inspired the famous ADS-CFT correspondence, linking gravity to quantum field theory. Out of the holographic principle grew one of the most important breakthroughs in modern physics, the ADS-CFT correspondence. Proposed by Juan Maldacena in 1997, it showed a precise mathematical duality between two seemingly different worlds. On one side was a string theory with gravity, living in a curved space called anti-de-Sitter space. On the other was a conformal field theory, a kind of quantum theory without gravity, living on the boundary of that space. Against all expectations, the two were equivalent. A universe with gravity could be fully described by a theory without it, written on its surface. This idea, born from string theory, provided a powerful new tool for exploring both gravity and quantum systems, bridging areas of physics once thought forever separate. ADS/CFT showed that a string theory in a curved space can be exactly equivalent to a field theory on its boundary. What makes ADS-CFT so remarkable is its precision. It is not a rough analogy or metaphor, but a mathematical identity. A string theory with gravity in a higher-dimensional curved space can be mapped exactly to a quantum field theory on the lower-dimensional boundary of that space. Every calculation in one theory has a counterpart in the other. Problems that seem impossibly difficult in one framework may be solvable in its dual partner. This duality turns some of the hardest questions about black holes, quantum fields, and even strongly interacting particles into problems with elegant answers. It is as though nature provides two completely different languages for describing the same reality, and physicists can switch between them as needed. This duality has been one of the most powerful tools in modern theoretical physics. Since its discovery, ADS-CFT has become a cornerstone of theoretical research. Physicists use it to probe black hole information, to explore the behavior of strongly interacting quantum systems, and even to model the early universe. It is one of the rare cases where string theory provides a precise and testable mathematical tool, rather than just broad speculation. The correspondence has been checked in countless ways, confirming again and again that the duality holds. For many, it is proof that string theory contains deep truths about the universe, even if those truths are not always easy to test directly. ADS-CFT transformed string theory from a bold idea into a practical instrument for solving some of physics' most enduring puzzles. It bridges black holes, particle physics, and even condensed matter systems. One of the most surprising applications of ADS-CFT is how widely it reaches. It was born in the context of black holes and curved spacetime, but it has been applied far beyond. In particle physics, it provides new ways to study the strong nuclear force, which binds quarks into protons and neutrons. In condensed matter physics, it has been used to model superconductors and strange states of matter that resist conventional explanation. Across disciplines, ADS-CFT serves as a kind of Rosetta Stone, translating problems between different areas of science. That a single correspondence could link the mysteries of black holes with the behavior of laboratory materials is a testament to the hidden unity that string theory reveals. String theory also explained black hole entropy in precise detail. Entropy is a measure of hidden information. For black holes, it is proportional to the area of the event horizon. But what microscopic states does this entropy count? For decades, this was unknown. Then, in the mid-90s, string theory provided the answer. By modeling a black hole as a configuration of strings and branes, physicists could count the possible arrangements that would give rise to it. Astonishingly, the number matched the entropy formula derived from thermodynamics. This was a moment of triumph, proof that string theory could explain one of the deepest puzzles of black hole physics. For the first time, black hole entropy was not just a formula, but a result of microscopic physics, with strings and branes as its hidden machinery. By counting the microstates of strings and branes, physicists reproduced the exact entropy formula. In classical physics, black holes are simple objects, described only by mass, charge, and spin. But string theory reveals a hidden complexity. The microstates, the possible quantum configurations of strings and branes that form a black hole, are countless. When physicists carefully counted these microstates, they found the result lined up exactly with the Bekenstein-Hawking entropy formula, which relates entropy to horizon area. This was more than coincidence. It showed that the mysterious entropy of black holes was not abstract, but real, grounded in the vibrations and arrangements of strings. It was one of the rare times when string theory made a concrete, calculable prediction that matched known physics precisely. This was one of the greatest successes of the theory to date. The ability to explain black hole entropy put string theory on a new level. For years, critics had argued that it was too abstract, too disconnected from reality. But here was a concrete triumph: the entropy of black holes, one of the most profound puzzles in physics, solved by counting string states. This success gave physicists confidence that string theory was more than beautiful mathematics. It could reach into the heart of real phenomena and provide answers no other theory could. It did not prove string theory correct as a whole, but it demonstrated that its tools were powerful, precise, and capable of explaining mysteries once thought impenetrable. It proved that black holes could be understood as collections of strings. In string theory, a black hole is not a singularity hidden behind a horizon, but a complex system of vibrating strings and branes. Each microstate is one possible arrangement of these fundamental ingredients. From far away, the details are hidden, and the black hole appears smooth and simple. But up close, in the theory's mathematics, the richness is clear. Black holes become quantum objects with enormous numbers of hidden states. This view reconciles them with the laws of quantum mechanics, preserving information instead of destroying it. What once seemed like the most mysterious and destructive objects in the universe become, in string theory, the natural products of vibrating strings at their most extreme. String theory hints that spacetime itself may not be fundamental. Perhaps the boldest suggestion of all is that space and time themselves are not ultimate ingredients, but emergent. In string theory, geometry may arise from the entanglement and relationships between quantum states. The smooth stage on which physics plays out could be a construct built from deeper rules. Just as temperature emerges from the motion of atoms, spacetime might emerge from the collective behavior of strings. If true, it means that our most basic assumptions, that space and time are fundamental, are illusions. The true fabric of reality could be something more abstract, woven from patterns of vibration and entanglement that we cannot yet fully describe. Instead, space and time could emerge from deeper quantum entanglements of strings. In recent years, physicists have used string theory and holography to uncover tantalizing links between spacetime and entanglement. The connections between quantum states may literally generate the geometry of space. Where entanglement is strong, space holds together. Where entanglement fades, space itself may tear apart. In this view, strings and their quantum relationships are not simply objects living in spacetime. They are the scaffolding from which spacetime itself is built. The universe, then, is not a stage, but a song, not a container, but a creation of patterns more fundamental than space and time. It is a vision that reshapes what we mean when we ask, what is reality? This view links string theory to cutting-edge ideas in quantum information. The discovery that spacetime itself might emerge from entanglement has connected string theory with a surprising new partner, quantum information science. Once thought of as purely practical, the study of qubits and quantum computers, quantum information has turned out to hold clues to the fabric of the cosmos. Using tools from holography, physicists have found that ideas like quantum error correction and entanglement entropy describe not just data, but space and time themselves. String theory has become a bridge between the geometry of the universe and the mathematics of information. It suggests that reality is not written in matter alone, but in relationships, codes, and patterns of connection, that the laws of physics might themselves be a form of quantum information processing. Entanglement patterns may literally weave the geometry of the universe. Entanglement is one of the strangest phenomena in quantum mechanics. When two particles are entangled, their states remain connected, no matter how far apart they are. In string theory, entanglement takes on a cosmic role. The strength and pattern of entanglement across quantum states may determine the shape of space itself. Where entanglement is dense and strong, space appears smooth and continuous. Where entanglement thins or breaks, space may warp, stretch, or even tear. This startling idea, known as equals epa, suggests that wormholes and entanglement may be two sides of the same coin. In this view, the entire geometry of the universe is not fundamental at all, but the result of vast webs of entangled strings holding reality together. String theory also predicts fields called moduli, tied to the shapes of hidden dimensions. Within string theory, the extra dimensions are not fixed and rigid. Their shapes can vary, shifting in subtle ways that change the vibrations of strings. These variations are described by fields called moduli. Each modulus corresponds to a degree of freedom, a possible way the hidden dimensions can stretch, curl, or twist. The presence of moduli means that the constants of nature, such as particle masses or force strengths, could in principle vary if the underlying geometry shifts. Stabilizing these moduli, preventing them from changing in chaotic ways, is one of the great challenges of the theory. Without stability, the universe itself could fluctuate uncontrollably, never allowing the consistent laws we depend on for stars, atoms, and life itself. These moduli could shift the fundamental constants of nature. The constants we take for granted, the charge of the electron, the strength of gravity, the speed of light, may not be constants at all. In string theory, they could be determined by the configuration of the hidden dimensions. If the moduli fields that describe those configurations were to change, so would the constants. That means the very rules of physics could drift, altering chemistry, stars, and life itself. Some theories suggest the constants we observe are simply the values set by our particular moduli. In another brane or another corner of the string landscape, the values might be entirely different. This possibility reframes what we mean by laws of nature. They may not be universal at all, but local, shaped by the geometry of dimensions too small to see. Stabilizing them has been one of the great challenges in the theory. The freedom of moduli fields is both a feature and a problem. Without stabilization, the hidden dimensions could constantly shift, dragging the constants of physics along with them. Our universe, with its stable atoms and chemistry, would not exist. To resolve this, physicists search for mechanisms within string theory that pin the moduli into place. These include fluxes, brane configurations, and quantum effects that lock the dimensions into specific shapes. The process is subtle and mathematically complex, but essential. Without it, string theory would predict a chaotic, ever-changing cosmos. With stabilization, it can explain why our universe has the constants it does, and why those constants remain steady over cosmic time. The search for stable solutions has become one of the central quests in string cosmology. The number of possible Calabi-Yau shapes is staggeringly large. Calabi-Yau manifolds, the candidate shapes for extra dimensions, are not a single object, but an enormous family of possibilities. Each manifold folds and twists in a unique way, producing a distinct geometry for the hidden dimensions. The number of such shapes is so vast that it defies imagination. Estimates suggest there may be more Calabi-Yau manifolds than atoms in the observable universe. Each shape could, in principle, host a different version of physics. Electrons, quarks, and forces might all behave differently depending on the manifold chosen. The sheer number of possibilities creates both a challenge and a wonder. Why does our universe correspond to one particular shape? And what would reality look like if the geometry were different? Each shape may produce a completely different universe with unique laws of physics. The geometry of hidden dimensions is not just mathematical decoration. It dictates the spectrum of particles, the strengths of forces, and the constants of nature. One Calabi-Yau shape might produce a universe with familiar physics. Another could yield a cosmos with entirely alien laws, where atoms cannot form or stars cannot shine. In this way, each possible shape corresponds to a distinct universe. Our world, with its chemistry and life, is one outcome among countless alternatives. This realization reframes the question of why the universe has the laws it does. Instead of being inevitable, they may be the result of a particular choice, one shape of many, hidden in the curled-up folds of dimensions we cannot see. This enormous diversity is known as the string landscape. As physicists explored the possibilities of hidden dimensions and stabilized moduli, they uncovered a staggering implication. String theory does not describe a single universe, but a vast landscape of possible universes. Each valley in this landscape corresponds to a particular solution, a combination of shapes, fluxes, and constants. The number of valleys may be so immense that it dwarfs even the total number of particles in the cosmos. This is the string landscape, a vision of reality where countless universes exist in theory, each with different physical laws. The landscape is both a challenge, making predictions difficult, and a source of awe, suggesting that our cosmos may be one among a near-infinite array. The landscape might contain more possible universes than atoms in the observable cosmos. Numbers quickly lose meaning when we talk about the string landscape. Estimates suggest the number of possible solutions could be 10 to the power of 500 or more, a figure so vast it cannot be compared to anything in everyday life. Even the number of atoms in the observable universe, around 10 to the power of 80, is tiny in comparison. This means that the diversity of possible universes within string theory dwarfs the contents of our own cosmos. Somewhere in that immensity lies a configuration that matches our world, but surrounding it are universes beyond imagining, each with its own constants, particles, and dimensions. If the landscape is real, our cosmos is not unique, but one grain of sand in an unimaginable ocean. Each valley of the landscape corresponds to a different set of physical constants. The string landscape is often pictured as a mountainous terrain, filled with valleys and peaks. Each valley represents a stable solution, a possible universe. In one valley, the constants may yield stars and galaxies. In another, the laws may forbid complex structures. Our universe is thought to sit in one of these valleys, stabilized by the configuration of its hidden dimensions. The constants we observe, the fine structure constant, the mass of the electron, the strength of gravity, are the markers of our valley. Somewhere else in the landscape, other valleys host universes with entirely different rules. The vastness of this terrain challenges our ability to make predictions, but it also opens the door to the idea that the laws of nature are not unique, but local features of a cosmic geography. Some physicists link this to the idea of the multiverse. The vast string landscape, with its countless possible valleys and universes, naturally connects to the idea of the multiverse. If each valley corresponds to a unique set of physical laws, then our cosmos may be just one realization among many. String theory does not require that we live in the only possible universe. Instead, it suggests that reality may be broader, a vast field where different regions settle into different valleys. This view shifts our perspective. The laws of physics are not uniquely determined, but chosen by circumstance, like one melody played among endless variations. For some, this is unsettling, removing the idea of a single necessary universe. For others, it is inspiring, hinting that the cosmos may be richer and more diverse than we ever dreamed. Our universe may be one bubble among countless possibilities predicted by string theory. If the string landscape is real, then each solution could correspond to its own universe. In cosmology, these are often pictured as bubbles, inflating and drifting in a larger multiverse. Our universe is one such bubble, with its constants and physics determined by the hidden shape of its dimensions. Other bubbles, formed from other shapes, may exist far beyond our horizon, forever inaccessible yet still real. Each bubble expands with its own version of physics, some barren, some unstable, perhaps a few capable of nurturing stars, galaxies, and life. String theory, then, may not describe a single universe at all, but an ocean of them, a cosmic froth where bubbles rise, expand, and drift in infinite diversity. Critics argue this makes the theory nearly impossible to test. The immensity of the string landscape and its link to the multiverse creates a serious problem. If there are countless possible universes, each with different laws, then how can we know which one is ours? And if most of them are beyond our reach, how can we test the predictions? Critics argue that this turns string theory into something unfalsifiable. Unlike Einstein's relativity, which produced concrete tests, string theory's multiverse implications seem forever out of reach. The worry is that a theory that cannot be tested is not science, but speculation. This has led to lively debates within physics, with some arguing that the elegance of string theory is not enough. It must find ways to make contact with experiments, or risk fading into philosophy. But supporters note it may explain why our universe is tuned for life. Supporters of the landscape view point to one striking fact. Our universe appears fine-tuned. The constants of nature seem delicately balanced, allowing chemistry, stars, and life. If they were even slightly different, existence as we know it would be impossible. Why should the universe be so precisely set? In the landscape, the answer is simple. There are countless possible universes, most of them inhospitable. We live in one of the rare valleys where the constants happen to permit life, not by design, but by selection. This is called the anthropic principle. We observe a universe suited for life because we are here to observe it. While controversial, this explanation turns what once seemed miraculous into something natural within the vast diversity of string theory's possibilities. String theory has also reshaped pure mathematics. Even beyond physics, string theory has had an extraordinary impact on mathematics. In trying to describe strings moving through curved dimensions, physicists encountered deep problems in geometry and topology. Their solutions often revealed hidden structures unknown to mathematicians. Entirely new branches of mathematics, such as mirror symmetry, were born from string theory's equations. Questions that had remained unsolved for decades suddenly found elegant answers through the lens of strings. In this way, string theory has become not just a physical theory, but a source of mathematical discovery. Its influence has spread across fields, showing that the pursuit of fundamental physics can transform even the most abstract realms of thought. It has solved problems in geometry, topology, and even number theory. Mathematics thrives on patterns, and string theory revealed patterns no one had expected. In geometry, it explained surprising relationships between seemingly different shapes. In topology, it uncovered new classifications of surfaces and higher dimensional spaces. Even in number theory, one of the oldest branches of math, string theory inspired fresh approaches to problems about symmetry and modular forms. These solutions were not always the main goal. They emerged as byproducts of trying to understand vibrating strings in hidden dimensions. The result has been a profound cross-pollination. Physicists borrowing tools from mathematics, and mathematicians discovering new theorems sparked by string theory. The boundary between the two disciplines has blurred, creating a shared landscape of discovery. Entire fields of math have advanced through questions raised by string theory. Perhaps the most striking example is mirror symmetry, a phenomenon uncovered by string theory. It showed that two seemingly different Calabi-Yau manifolds could produce identical physics. This implied a deep symmetry in mathematics itself, one that had never been suspected. Mirror symmetry grew into an entire field of study, producing new results and methods across geometry. Similar advances appeared in knot theory, algebraic geometry, and the study of moduli spaces. String theory's speculative attempts to describe the universe ended up driving entire branches of mathematics forward. For many mathematicians, the theory has become as valuable for its mathematical insights as for its physical promises. Mathematicians and physicists now collaborate in unprecedented ways. In earlier eras, mathematics and physics sometimes drifted apart. Mathematicians pursued abstract structures, while physicists focused on experiments. String theory changed that. Its problems are so rich, so deeply mathematical, that collaboration became essential. Mathematicians work alongside physicists to explore Calabi-Yau manifolds, mirror symmetry, and topological string theory. In turn, physicists borrow sophisticated mathematical tools to handle the complex geometries of hidden dimensions. This collaboration has produced breakthroughs on both sides, forging bonds between fields that once seemed separate. In this way, string theory has reshaped not only our vision of the cosmos, but also the very practice of science itself. String theory also influenced studies of superconductors and exotic materials. Surprisingly, string theory's influence extends even into condensed matter physics, the study of materials. Using holography and ADS-CFT dualities, physicists have modeled systems that are otherwise impossible to calculate. This includes high-temperature superconductors, strange metals, and other exotic phases of matter. Though these materials live in the laboratory, their equations resemble those of strongly curved spacetimes. String theory provides a new lens for tackling these puzzles, offering insights that may one day lead to practical breakthroughs in technology. Once again, what began as a theory of the cosmos has rippled outward, touching unexpected corners of science. Through holography, it has provided tools to explore strongly interacting systems. One of the hardest problems in physics is dealing with strongly interacting particles. Traditional methods often fail, as the forces are too intense to approximate. Here, holography comes to the rescue. By translating these problems into the language of curved spacetime and strings, physicists can find new solutions. Systems that once seemed opaque become tractable. From quark-gluon plasmas to superconductors, holography has opened doors across disciplines. Though originally a tool for quantum gravity, it has become a universal method for studying complexity itself. The fact that a theory of tiny strings could illuminate everything from black holes to laboratory materials is one of the most surprising and inspiring outcomes of modern science. Even the physics of quark-gluon plasmas has been studied with string-inspired methods. Quark-gluon plasmas are the most extreme states of matter we can create in laboratories, fireballs hotter than 1 trillion degrees, where protons and neutrons dissolve into their constituent quarks, gluons. Such a plasma filled the early universe just moments after the Big Bang. Calculating its behavior is nearly impossible, since the forces are too strong for ordinary methods. Yet string theory, through holographic duality, has offered new tools. By translating the plasma into the language of black holes in curved spacetime, physicists can study its properties indirectly. In this way, string theory illuminates physics both unimaginably vast and minutely small, linking the behavior of cosmic singularities to droplets of matter created in particle colliders. The theory links phenomena across scales, from black holes to laboratory materials. One of the most astonishing features of string theory is its reach. A framework developed to explain the deepest structures of spacetime also provides insights into earthly materials, superconductors, and even exotic states of matter. Through holographic dualities, a calculation about black holes can inform questions about convectivity. Through vibrating strings, theories of the cosmos connect to phenomena only seen under microscopes. This breadth is part of why string theory has captivated so many physicists. It suggests that the universe is unified in ways we rarely suspect, that the same mathematics can echo from the interior of a black hole to the crystalline lattice of a lab-grown material. It dissolves boundaries, showing us that scale is only a matter of perspective. Despite its elegance, string theory has yet to make direct experimental predictions. This is the central challenge for string theory. It offers a dazzling vision of unification, but translating that vision into concrete, testable predictions has proven elusive. Strings are so tiny at the Planck length that no accelerator can probe them directly. Many of its implications, like extra dimensions or supersymmetric partners, remain beyond reach. This gap has fueled debates. Can a theory be considered scientific if it cannot be tested? Supporters argue that predictions may come in time as technology advances or as indirect evidence accumulates. Critics counter that decades have passed without verification. For now, string theory exists in a peculiar limbo, an elegant mathematical structure whose truth remains tantalizingly out of reach. Supersymmetric partners have not appeared in the Large Hadron Collider. Supersymmetry is a cornerstone of modern string theory. It predicts that every known particle should have a heavier partner, electrons paired with selectrons, quarks with squarks, and so on. The Large Hadron Collider at CERN has searched for these particles in its high-energy collisions, hoping they might appear just beyond our current reach. Yet so far, no supersymmetric partners have been found. This absence has troubled physicists, forcing revisions to earlier hopes. Perhaps the partners are much heavier than expected, hiding beyond the LHC's limits. Or perhaps supersymmetry, at least in its simplest form, is not realized in nature. The silence from the collider is one of the greatest puzzles facing string theory today. No evidence of extra dimensions has been found so far. Another bold prediction of string theory is that reality may include hidden dimensions beyond the familiar 3 of space and 1 of time. These extra dimensions, curled up so tightly they escape detection, could shape the very laws of physics. Experiments have searched for signs, subtle deviations in gravity at short distances, or missing energy in collider events hinting at particles slipping into unseen directions. Yet no evidence has emerged. Like supersymmetry, the extra dimensions remain speculative, supported by mathematics but not yet by data. Their absence has led some to question whether they exist at all, or whether nature has chosen a different path than string theory imagines. This absence of data has led to criticism of the theory. For all its elegance, string theory faces a constant refrain. Where is the evidence? Critics argue that decades of research have produced stunning mathematics, but little empirical support. Without data, they say, string theory risks becoming metaphysics, beautiful but untethered from the physical world. Defenders reply that great theories sometimes precede evidence by generations. Einstein's predictions about gravitational waves took 100 years to confirm. Perhaps string theory is in a similar phase, waiting for the right tools. Still, the lack of experimental grounding remains the sharpest point of contention, casting a shadow over its extraordinary promises. Yet indirect clues may still emerge from cosmology. If colliders cannot probe strings directly, perhaps the universe itself can. The cosmos acts as a natural laboratory, having reached energies far beyond anything human-made in its earliest moments. Cosmology offers subtle clues, patterns in the cosmic microwave background, the distribution of galaxies, or the ripples of gravitational waves. These may carry faint signatures of string theory's hidden dimensions or early universe dynamics. Physicists scan the sky for these whispers, hoping that cosmology can do what particle colliders cannot: open a window into the stringy foundations of reality. Primordial gravitational waves could carry the fingerprints of string theory. Gravitational waves, ripples in space-time, have already been detected from colliding black holes and neutron stars. But primordial gravitational waves, created in the universe's earliest instance, may still echo faintly through the cosmos. If string theory is correct, these waves could carry distinctive signatures of extra dimensions or brane interactions. Detecting them would be extraordinarily difficult. They would be faint and tangled with cosmic noise. Yet experiments continue, with sensitive detectors scanning the heavens. A confirmed signal would not only reveal the universe's birth pangs, but might finally tie string theory to observable reality. Hypothetical objects called cosmic strings may also stretch across the universe. Despite the name, cosmic strings are not the same as the fundamental strings of string theory. They are hypothetical one-dimensional defects in space-time itself, relics from the early universe. Some versions of string theory predict their existence. If real, they could stretch across cosmic distances, as thin as an atomic nucleus but heavier than mountains. They might reveal themselves through gravitational lensing, bending light around their invisible threads, or through bursts of gravitational waves as they vibrate. Discovering one would be revolutionary, a direct link between the mathematics of string theory and the fabric of the cosmos. These relics, if found, would be striking evidence for the theory. Cosmic strings would stand as fossils of the universe's earliest moments, proof that the hidden dimensions and symmetries of string theory once shaped reality in ways we can still detect today. Their discovery would transform string theory from speculation into experiment, anchoring its equations in observation. For now, they remain hypothetical, searched for but unseen. Yet their possibility lingers, a tantalizing reminder that the universe may still hold surprises vast enough to confirm ideas born from the tiniest of strings. Some versions predict that tiny black holes could form at high energies. In certain versions of string theory, if extra dimensions exist and are large enough, gravity could become stronger at very small scales. That would mean high-energy collisions, far less powerful than the Big Bang itself, might be able to create miniature black holes. These black holes would be fleeting, evaporating almost instantly, but their creation would reveal that space-time itself bends and folds at the scales string theory describes. So far, no such micro-black holes have been seen, even at the Large Hadron Collider. But the possibility remains one of the most dramatic experimental consequences of the theory, that a collider could briefly open windows into the deep quantum structure of space-time itself. Detecting them would reveal quantum gravity directly. The union of quantum mechanics and gravity has long been the holy grail of physics. If tiny black holes could be created and observed, they would radiate away through Hawking radiation, producing distinct signatures of quantum gravity. This would not only confirm the existence of extra dimensions, but would also place string theory, or some cousin of it, firmly into the realm of experimental science. Such an observation would be as momentous as the discovery of relativity or quantum mechanics themselves. Though the search has so far turned up nothing, the dream of capturing a direct glimpse of quantum gravity continues to drive experiments and inspire bold imagination. String theory remains the most mathematically complete approach to unifying physics. Even without experimental proof, string theory holds a unique place in science. No other framework has woven together the fundamental forces of nature so seamlessly, incorporating quantum mechanics and gravity into a single, consistent whole. It is dazzlingly rich in mathematics, generating connections between fields as diverse as geometry, topology, and number theory. These discoveries have not only influenced physics, but have spilled over into pure mathematics, where results inspired by string theory have solved problems once thought impossible. It is, at its core, an extraordinary intellectual achievement, whether or not it describes the literal fabric of our cosmos. It continues to inspire new generations of physicists and mathematicians. Beyond its equations, string theory's greatest legacy may be inspiration. It has drawn countless students into physics and mathematics, captivated by the idea that reality itself might be written in the language of vibrating strings. Research groups across the world continue to explore its mysteries, building careers and communities around its questions. For many, it represents the dream of physics, that the universe is not a patchwork of separate laws, but a unified whole, waiting to be uncovered. The allure of that vision ensures that string theory, whatever its fate, remains one of the most influential ideas of our age. Even if string theory is not the final answer, it has transformed our understanding of space and time. The theory may never be proven correct in the way we hope, yet it has already changed physics forever. It has forced scientists to confront the possibility of hidden dimensions, new symmetries, and strange dualities between seemingly unrelated theories. It has made us rethink what it means for spacetime to be continuous, smooth, or fundamental. In this sense, string theory has already succeeded. It has expanded our imagination of what the universe could be, laying pathways for discoveries we cannot yet predict. Its impact extends beyond proof into the very way we think about reality. It has revealed deep connections between seemingly unrelated areas of physics. One of string theory's greatest gifts has been its uncanny ability to link distant corners of science: black holes and fluid dynamics, nuclear plasmas and curved spacetime, condensed matter and quantum gravity. Through its web of dualities, string theory has drawn lines between subjects that once seemed disconnected. These links have opened new fields of study, turning mysteries in one area into solvable puzzles through another. This unifying power suggests that nature itself is woven together more tightly than we ever suspected, with strings and branes providing the threads of the cosmic tapestry. It has shown that gravity and quantum mechanics need not be enemies, but partners. For much of the 20th century, gravity and quantum theory seemed irreconcilable. Every attempt to merge them collapsed into contradictions and infinities. String theory changed that. By replacing point particles with strings, it smoothed the violent short-distance behavior of spacetime, making a consistent quantum gravity possible. In this picture, gravity is not an afterthought, but an inevitable outcome, woven into the very vibrations of strings. Instead of enemies, quantum mechanics and gravity emerge as complementary, two sides of the same reality. It has made us rethink what is meant by dimensions and particles. The everyday concepts we rely on, that space has 3 dimensions, that particles are tiny points, are revealed in string theory to be approximations, not absolutes. Dimensions may be hidden, curled, or emergent. Particles may be nothing more than the shadows of vibrating strings, their properties determined not by arbitrary rules, but by the music of higher spaces. To study string theory is to realize that even our most basic intuitions about reality are provisional, waiting to be redefined by deeper understanding. It has expanded the very idea of what a universe can be. From branes colliding to multiverses branching, string theory offers visions of reality far beyond what we once imagined. Our universe may be only one bubble among countless others, or a vibrating membrane drifting in higher dimensional space. The cosmos could be stranger than any myth or story, its laws shaped by the geometry of spaces too small for us to see. String theory stretches the imagination, teaching us that the word universe might not capture the full vastness of what is. And whether or not it is proven true, string theory has changed forever how we imagine reality itself. In the end, string theory's ultimate legacy may be philosophical. It has shown us that the universe can be envisioned in astonishingly new ways, with extra dimensions, vibrating strings, and hidden symmetries binding all of nature together. Even if future discoveries replace it, the imprint will remain. It has already shifted science into a new mode of thinking, where unification, beauty, and mathematics are as central as experiment. In this sense, string theory has succeeded. It has given us a new imagination of reality, and with it, a reminder of how wondrous and infinite the quest for knowledge can be. And so our journey comes to a close. We've wandered through hidden dimensions, listened to the vibrations of strings, and stood at the edge of black holes. From the smallest scales of quarks to the wide horizon of the cosmos, string theory has carried us into visions both daring and beautiful. Perhaps one day it will be proven true, or perhaps it will give way to something even deeper. But in either case, it has already reshaped how we imagine reality. It has shown us that the simplest things we take for granted, space, time, and matter, may hold secrets far beyond our sight. And in that mystery lies wonder, the kind that lingers even as we drift toward rest. If you've enjoyed this quiet journey, I'd be grateful if you left a like, or subscribed, or even shared your thoughts in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, you don't need to do anything at all. Let your breath slow, let your body sink into stillness, and let your mind grow soft and weightless. Like strings humming gently in hidden spaces, let your thoughts fade into silence until sleep comes to carry you home. Good night.